biochemistry series. Today we're going to be going back to episode 2 and talk about electron configuration. Here are the 4 blocks: S block, D block, F block, B block, principal, diffuse, sharp, and fundamental. Very important. And well, they are important. The F block is disconnected only to save space. You see, it's to save space. There's no scientific reason. Just like Alaska and Hawaii, because it's too big. Now these are the radioactive elements. We're going to talk about this later in episode 23. We will learn more about radioactive elements, of course. Now we just destroy them. We can understand a lot about biochemistry by drawing the orbital shells of atoms. Elements boron, neutron, neon have 2 shells. We can learn even more by understanding subshells of the atom. Let's see how the periodic table teaches about these subshells. So, you see here, but however, let's look at boron. Right here, 1, 2, 3, but now you look like there's sort of 2 outer shells. So there's inner outer shell and just outer shell. This is not very scientific. Let's just learn about it. On the inner shell, we have 2 electrons. And then on the outer shell, we have 1. What about this? 1, 2, 3, 4. 1, 2. You will notice that all the inner outer shells both have 2 electrons, while the outer shells fill up to 6. Yeah, these are the subshells. So here's 1s, 2s, 3s, 4s, 5s, 6s, 7s. 3D, 4D, 5D, 6D, 2P, 3P, 4P, 5P, 6P, 7P, and 4F and 5F. The periodic tables block test where each subshell begins and what it is named. Here's 1s, 2s, 3s, 4s, 3D, 2P, 3P, 4P. So here's hydrogen, and it's single electron. The same. This is 1s1, so here's the hydrogen again. This one is then the 1s represents this. So the big one represents the shell. The 1 represents the number of electrons. And then for helium, it's the same thing. 2 electrons. What is it? 1s2 because 1s shell and 2. So 1s, 2s, 3s, 4s, 3D, 4p, 3p, 2p. What about lithium? Well, now we're at the 2s, so it's going to begin with 2s, but first we need to fill the electron shells. These are the same. 1s2 because we want to fill 2s1. Now what about beryllium? Well, we do the same thing. We add the shells, fill in the electrons, and then we have 1s2, 2s2. But now comes boron. It's a little bit more different. You see here, same thing, but we add an extra outer shell because we're the 2p. The reason is because 1s2, 2s2 through p1. You notice 1s2, 2s2, 2p1? It's because you see there are different orbitals. Every time you have a new orbital, you put them there. So it's close because they're on the same energy level or same row, but they're different subshells. These are known as subshells. We are using superscripts, just so you know. Same thing for carbon. We add this outer shell. 1s2, 2s2, 2p2 this time. Same thing. 1s2, 2s2, and 2p3, of course. Remember that it is always 2s. You notice the elements on each. So the reason it can only hold 2 electrons because there are only 2 electrons here. It can hold this much, you know. You get the point, probably. This is oxygen. And then we have 1s2, 2s2, and 2p. Guessed it? 4. What about fluorine? Same thing. We fill in the S2s, 2p, 1s2, 2s2, 2p4, 5 actually. Same thing, 1s2, 2s2, and 2p6 because we're on a 4 shell. So you probably got the point of this sort of inner shell. this is the different part, as you can see here. So you have this 2s2 and this 2p1 sort of extra shell. Here's the element names, electron configuration of those 3 elements. So here are the orbitals, but we add the new level because we're on the 3rd row. Here's the electrons. And then you can clearly see 1s2, 2s2, 2p6, 3s1. Because we're here, not here. Same thing for. But now, what element is this? Here are the electrons, the orbitals, and the electrons. What element is this? What element? So what element was I? So what element is this? This is sulfur. So it's very similar to oxygen because it's right below it, sort of like the father of oxygen, even though it's not. It's chemically similar, but it's physically different. 1s2, 2s2, 2p6, 3s2, 3p4. We have this. Element is argon. By the way, try to guess the electron configuration before I show it. Try to guess the electron configuration. This is great practice. Write it down. Draw. There's not a lot of timer, but we're just drawing. The electron configuration is, drumroll please, 1s2, 2s2, 2p6, 3s2, 3p6. Now that was a little too dramatic, but what are the electron configurations for the following elements? I'll give you a few seconds to ponder it. Feel free to pause the video. Okay, if you pause the video, okay. Here are the answers. Magnesium, 1s2, 2s2, 2p6, 3s2. Aluminium or aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. Silicon, 1s2, 2s2, 2p6, 3s2, and 3p2. Phosphorus is 1s2, 2s2, 2p6, 3s2, and 3p3. What about chlorine? Drum roll. 1s2, 2s2, 2p6, 3s2, 3p5. How many bonds would each typically make? Count the lone outer electrons. Feel free to pause the videos again. Well, look at the outer electrons. You will notice P, S, and chlorine are often colored in models, just so you know. Sodium. So you will notice each of these have 1, 2, 3, typically 4, 5, which is hypervalency. Fancy word. So we're going to talk about it in the next episode, episode 13. This is episode 12. What about sulfur? It usually takes this, but that's hypervalency. It's only 2. Hypervalency, chlorine 7, and argon 8. Sodium vapor emission. Sodium vapor lamps is to outer the electrical orbital range where sodium atoms to generate light. Sodium vapor lamps passing electricity through vaporized sodium excites an electron from 3s to 3p. The electron then falls back to 3p to this and gives out yellow light in the process. 1s2, there's 3p0. It can go on forever. 3p0, it can be 4s0, 3d0, 4p0, but we don't do that. Look. So look back. We have 3s1. When you pass the electricity, the electron moves to the next orbital. Then it jumps back, releasing yellow light. So let me do that again. Electricity passes through. 3s1 turns to 3s0 and 3p1. Then it falls back, releasing yellow light in the process. And that is sodium vapor. Other gases would give different color light emission, just so you know. Sodium emission is visible from the space station, as you can clearly see here. The first sign of intelligence of visiting from another planet would see, and the approach Earth is the light from sodium vapor lamps. What about 4s? Potassium? We need to add just extra 4s1 and calcium. 4s2. Electron configuration of scandium. You notice that it's 3D. The reason that begins with 3D because 3D is much stabler than 4D. So it often goes, this is the fifth electron to be added on the third level, not on the fourth. This is a lot of things, but this is how the universe works. Scandium. Notice it's here, not there. That zinc here, it's a full. It has a full thing. Magnesium, iron, cobalt, nickel, copper, zinc. So 4, 6, 8, 10. So that's the electron configuration. Zinc has 3D orbitals. They're several very stable. This configuration is sometimes called the pseudo noble gas configuration. Pseudo means like, so it's like noble gas because it has a full shell, though it's not a noble gas. Now, electrons fill the D block as expected until chromium, titanium, vanadium, chromium. Chromium prefers to have a 3D orbital, giving the manganese configuration, and this is by stealing an electron from the fourth orbital, so cancel that calcium. Vanadium, you notice? So electron from here says, I'm not going to be here. I want to be there so we can be stable. Let's go. Then it goes there. Now, the stable half-way 3D orbital without the need for stealing an electron from the fourth orbital. Manganese has a typical electron configuration. Electron fills the D block as expected until Cu, iron, cobalt, nickel, copper. Wait! Copper refers to the 3D orbital, giving the Z in configuration. This is by stealing an electron as the fourth orbital, similar to chromium. Zinc has a stable, and so it's perfectly fine. Electron configuration of 3D elements. See, focus on. Once the fourth substrate electron enters the lower 3D substrate, this product is then explain this to us. We just need to remember that the first D electron is a part of the third shell, not the fourth. Filling the 4p substrate. Filling the D blocks filled 4p electrons add into the way 4 shells. Expect this way is 4 boron to neon and aluminium to argon. Gallium, germanium, arsenic, selenium, bromine, and krypton. Here are the periodic treatments. Helium, neon, and argon consider noble gases because they have a complete Earth stack. Zinc has a pseudo-noble gas configuration, so it has a filled 3D shell. What other elements are noble gas? The rest of the elements have the pseudo-noble gas electron configuration. I'll give you a moment to ponder just that. Don't forget, it's okay if you pause the video. Well, these are the pseudo-noble zinc, cadmium, mercury, and carbon, and the noble gases are helium, neon, argon, krypton, xenon, radon, organism. And while zinc, cadmium, mercury, and carbonesium are similar. Periodic twins, neon, argon, krypton all have 6 p electrons. These elements do not make bonds with other elements. What about fluorine, chlorine, bromine? Or S and C? What about these? In the next lesson, we'll begin to learn the chemistry of S and D block metals. Homework. Practice writing the electron configuration once to say you don't have to draw the orbit. Just write the electron. For example, 1 2 2 2 p6 3 p 4 4 so forth. And then one thing is to notice before is that about this is where we go backwards. Let me go back. There's a shortcut called the noble gas shorthand, in which you find the closest noble gas. So, for example, if I was looking for sodium, the closest would be argon. So I'd write argon bracketed, then the rest of the electron configuration. For example, aluminium, the closest is neon. So I'd write neon bracketed 3s2 and 3p1, just so you know as a side note. And this is your homework. You can pause the video. And then this is it. And we'll see you later. Bye for now. Don't forget to subscribe and follow me on Instagram and Facebook. Bye. Don't forget to subscribe.